All right, I'm assuming this works. So, cześć wszystkim, welcome everyone on the second Web3 Krakow meeting, again in our Software Mansion office in Krakow. So I'm Arthur from Software Mansion. I'm working on the Starknet team, and I'll be the host for today. So we'll have 3 talks as previously, and we just start them in a minute, but I'll just go through some, let's say, technical details, so I'm sure everybody knows everything. So first of all, there are beers and other drinks in the kitchen. There's self-service of sorts, so feel free to just go there and grab anything at any time. We'll have pizza and some time for the just talking and networking after the talks. So it will be in around 2 hours from now, hour and 30 minutes maybe. If somebody needs to go to the restroom, they are just close to the entrance. You enter the office. You have to just go to the left from the entrance. They're there. And after every talk, we'll have some time for the questions. So if you have any questions, just feel free to wait and ask them at the end. So first, we'll have the talk hosted by Yuval from Starkware, and he will introduce us to Cairo programming language. So off to him.
Okay, so you can see me, I guess, right?
Yeah, we hear you. We hear you.
Great. You can see me as well, right? Let me share my screen. And I will start. So I think it's the same problem I had before, so sorry about that. Okay. Can you see me? Can you hear me?
Yeah, we do hear you.
Okay, great. Okay, so hi, I'm Yuval from Starkware. I'm an engineer on the compilers team. So we are working on Cairo. We developed Cairo and its compilers, compilers in plural. I will mention why I say in plural in a few minutes. And I will today talk about what Cairo is. Just before I start, I just wanted to mention that we work closely with Software Mansion. One of the key components of the Cairo language is the package manager, which is SCAR. So if anyone knows Rust, then it's the equivalent of Cargo. Yeah, so this is our relation with Software Mansion, and I want to ask who knows some things, but I don't. Okay, maybe I only see. I cannot pin you in the presentation, so maybe after I ask someone talk, so that the presentation changes. So who in the crowd, the audience knows Starknet or what Starknet is?
There are some raised hands, so yeah.
A little, okay. And Rust? Again, I don't see, so just
Some people raise hands, so.
Okay, anyway, so whoever knows Starknet, great. Whoever doesn't, I will mention it in a few words, but it's mostly out of scope in this talk. So you have to take the purpose as granted. And for Rust, you don't need to know Rust, but if you do, then it will be easier for you because there are similarities. Okay, so let me start. So as I said, I'm Yuval. But one more thing is I want to introduce you to my dog. This is Skippy. He's 2 years old. As you can see, he likes to eat stuff. but his favorite snack is ice. So this is, for example, for his first birthday when we made him an ice cake. Yeah, and you might think it's not important, but trust me, it will be important later. So, okay. So this is what I'm going to talk about today. So first, what Cairo is and why we need it. Then how it looks like. Something about some stuff about Cairo contracts, some basic knowledge about it, and then what's coming up. Okay, so let's start with what Cairo is and why we need it. So Cairo is a high-level Turing complete language for creating star-provable code. It might be might seem like a complicated sentence, but if we break it, then high-level language, you know, like a language that everyone can use and easily and friendly develop in. Turing complete language means you can develop any computation you can do with any other language with it. And start for creating star-provable code. So this is the starting part. What we do is to we take Cairo code is translated eventually to some set of polynomials, which then are proven to have a solution in the star protocol. So this is what StarkNet does, and the StarkNet has Cairo contracts. So all the contracts in StarkNet can be proven to run and get some result. So this is like in few words about StarkNet. If you do have questions, feel free to ask even in the middle because it's important. So I will try to answer with as few words as I can, but this is important to understand at least for the scope. If you know Cairo 0, so this is the predecessor of Cairo. Cairo is the successor and the improvement of Cairo 0. If you don't, that's completely fine. I will describe Cairo anyway. And this is Rust inspired, as I said. So the syntax might look very similar to whoever knows Rust. There are differences, but I will talk about them too. And the most important thing about it is that, again, it's a high-level, very friendly language, very modern language to write both general purpose code and also contracts, smart contracts for StarkNet. Yeah, and again, if you know Rust, the importing to Cairo may be much more easier for you. You also can know that it's open source, so it's on GitHub. You are welcome to take a look, review, suggest issues, contribute, etc. We're very welcoming that, and we look forward to it. So feel free to do that. And there's a lot more on the roadmap, so stay tuned to it, and I will mention some of it later in this talk. Okay, so why we need Cairo? So as I said before, we have Kazem. I didn't say Kazem, but what we do is what we have is Kazem. Kazem is Cairo assembly. It's actually an assembly language that is translated directly or almost directly to the set of polynomials that are used in the star protocol. So if we translate the Kazem to the polynomials, then using stars, we're able to prove that a program in Kazem ran or not and gave the result, the set result. But this is an assembly language, as I said. And what we want to add on top of it are two important features. The first is safety, and the second is ergonomics. And by safety, I mean that every Cairo program needs to be able to be proven that it ran, even if it failed. So I will I will dedicate a minute for it. So previously in Cairo 0, for example, and in Kazem as well, because it's an assembly language, we had this problem of if a program runs but then fails, it is not possible to prove it. And this is problematic in, for example, I will give you two examples. The first is we can be exposed, the prover can be exposed to a DDoS attack. So if someone malicious wants to DDoS the prover, what they need to do is to send transactions that will trigger programs that fail. What it means from the prover point of view is that it runs the program, it fails, and then it cannot prove even that it ran the program, so it cannot also take the fee for it. So we just use its resources and for nothing. So this is efficient for DDoSing the prover, and we want to avoid that. And the second thing is, if we are not able to prove that we ran the program and it failed, we cannot claim that we don't censor anyone. So from whoever sends the transaction cannot tell if you ran it and it failed or we just didn't run it. So being able to prove it helps us claim that we don't claim and prove that we don't censor anyone. And the second thing is that we want ergonomics, of course, to make it a high-level friendly language. So we do it by two layers. So the first layer is Sierra. So Sierra stands for Safe Intermediate Representation. And what it actually does is a language, relatively low-level language as well, that compiles into Kazan, to the Cairo assembly. But what the guarantee that we get is that every program written in Sierra is compiled into safe Kazan. And again, safe in the meaning that I just described. So every Kazan code that is resulted from Sierra compilation can be proven even if it fails. And the second layer would be Cairo, which adds the ergonomics, and this is a high-level language. So what we get is Cairo, that is a high-level language that compiles into Sierra, that compiles into Kazan, which is also always a safe Kazan that can be proven. So this is what we want from Cairo, and this is what it has. Any questions so far before I continue? I don't see anyone, so you need to talk if you want to ask. Okay. Again, feel free to interrupt if you have any questions. Also, there will be time, yeah. Okay, so how it looks like. I'm gonna show you the basics of how the code looks like. It's a limited time, so we don't really have the time to deep dive into everything. So just a taste. But again, more important is for you to understand the capabilities and what Cairo gives you, and then it's very similar to other very modern languages that are easily that are easy to program with. Okay. So this is the very basics. It's very similar to Rust. I think it's even maybe exactly the same as Rust in this case. So these are some basic idioms. You can see we have, as any high-level language, we have uses, we have constants, types like enums and structs. Enum is a Rust concept if you know other languages, so you might not be aware of exactly what enum is in this context, but it's not complicated. It's not something interesting. Comments, variables, all the variables are by default immutable. This is mostly because our behind the scenes Kazan has an immutable memory layout. And if you want a mutable variable, then you can use the keyword mute. And this simulates something over the immutable memory layout that we have. We have inner matching, again, like in Rust, functions, literals, and so on. Yeah, so this is the very basics. I'll go on again if you have something to add. This is a little different than Rust. So far, it was very similar. So we have traits and impulse. So Rust also has this concept of traits, but in Cairo it's a little different. So for whoever doesn't know Rust, trait is somewhat like an interface. So for example, here in the ice eater trait, what it means is that whoever will implement this trait has the function eat, needs to implement the function eat ice. So for example, in this implementation, ice eater dog, we implement, this is an implementation of the ice eater trait for the struct dog in this case. This is very similar to Rust. As you can see, we use we first name the impel, and then we also use the keyword of instead of for, because a trait is not implemented for a struct, it is just implemented, and it has a set of generic parameters which can be used for this purpose. So in this example, with one generic parameter, it's very similar to what Rust has. And the difference is mainly to have much more flexibility in the input. So first, naming inputs is important and helps do stuff. And also having few or multiple generic arguments, for example, can let you have few functions with different self-types. So this is one thing, but it generally gives you some more flexibility over what Rust has. So in this implementation, we have an implementation of the eatIce function. And as you can see, we have a self parameter, a parameter named self, and another parameter. So they are almost similar, but the fact that the self parameter can be used to use the dot operator. And as you can see below in main, actually, I'm not, this is going to be better for you. Right, you see large enough. So here we call skippy.eatIce, and skippy is passed as the self parameter, and minutes is passed as the time parameter. So if we have self, we can use the dot operator. And one more important difference from Rust is that we can define the implementation of a trait everywhere in the program, and not specifically in the context of either the trait or the type. So in Rust there is some limitation, we don't have it. Okay. Rare parameters are a way to change values of variables in a function so that it affects the call side. So just like other references in other languages, but in our case, again, as I said before, we have an immutable memory layout. So it's not actually changing the variable in the memory. What's actually happening is this is simulating receiving a parameter, an immutable parameter, and returning a new parameter that will be bound into the same variable that was outside of the method call or the function call. So in this case, we have two ref parameters. I'm saying it because it has some hidden cost that you need to be aware of. It's not substantial, but if you try to optimize optimize the minor things that you might need to know that. But in general, this hides this thing from the user because it's easier and more friendly. So it can be seen as an actual ref, but this is what actually happens behind the scene. So here we have self and ice amount as two ref parameters in the trait ice eater. And again, we have the struct dog and the implementation ice eater dog of ice eater with the type dog. And as you can see below again in main, we define Skippy as an instance of a dog. and ice amount. They're both mutable. Otherwise, if they weren't mutable, we could not pass them as ref parameters into the functions, because ref parameters means we are able to change the value inside the function, and it doesn't make sense if the variable in the call side is not mutable. And then you can also see we enforce the ref keyword also in the call side. So we have to mention ref here to be able to pass the parameter. There is one exception, which is the self parameter. So in the self parameter, we don't need to mention that this is the ref parameter. This is implicit because it's easier and more convenient to the user. Okay, any questions?
We have one question, I think.
Sure.
Now the microphone works.
Yeah, actually, I have a comment about like
I'm not talking to myself.
the previous stuff. So because like my question is more about like why do we need the provability of the program? Is this because like in Ethereum or Bitcoin we would send a transaction and that would be executed on multiple nodes, and here we can just execute it on one and then prove it by other nodes? Is that the reason?
So StarkNet is a layer 2 rollup, a ZK or validity rollup, if you know what it means.
More or less. I mean,
okay,
I know a bit about zero knowledge proofs, but not about rollups itself.
Yeah. So okay. So validity equals ZK in this sense, and rollups means that what we do is that we're a second layer over Ethereum, and what we do is we do some computations or aggregate some, like I say it really in the big 10,000 feet overview. So we aggregate a lot of transactions. We take them. I forgot a word. Sorry. We put them in a one small proof. We aggregate all of them to a one small proof, and then we post this proof onto the layer 1 Ethereum. So if the proof is advertised in layer 1, then you know that the state has changed from the old state to the new state with much less data. So this is much less expensive than posting all the transactions on layer 1.
Okay, thanks. My second question is about like, so if this is like a Turing complete language, how do you actually make it so that you can't really like halt it? I mean, so that, you know, the prover won't be DDoSed. I think you kind of maybe explained it, but I didn't get it.
So, for example, the idea is that we want to prove that the program ran and there is some result for it. So if there was some actual result, it succeeded and there is a result, then we have chart is exactly the protocol to prove this stuff. This is a little complicated, so again, I'm not gonna get into these details, but there are many resources online, so you're welcome to read them. And the idea is that we also want to be able to prove that we ran a program and it didn't get any result, so it failed. So what we do is something like, if you can think of it as, instead of failing, instead of exiting the program in some places, we change this exit with an error to a return false. Okay, so every success flow returns true with some value, and every failure flow returns false. So we actually change it to always succeed with some value. Some of the values reflect failures, and then we are able to prove that the program ran and resulted in this result. It's much more complicated than that, but this is the basic idea.
Okay, thanks.
Yeah, sure. Great. Thanks for your questions. Okay, let me go on. So these are parameters, snapshots. So snapshots are a new way to pass variables into functions as parameters. So far we had two options to pass variables to functions. One was by value, and the second was by ref. So by value, if we pass a variable by value, we also pass the ownership of this variable into the function. So in Cairo, because of the immutable memory layout, and because we have a linear type system. If you want to read about linear type system, I recommended it. It's interesting. But the basic idea is that every variable is created and then can only be owned and needs to be used exactly once. Okay, so if I have a variable, I need to either drop it, which means I use it, or pass it to someone else, which will take ownership on it and will be responsible to drop it. So in the end of the program, we are not able to remain with any undropped variables, and so we need to use all of them. Okay. So if we pass a parameter, this is also somewhat similar to Rust. So if we have ownerships on the variables, and if I pass the ownership to a function, then I cannot use it later myself. So if, for example, I want to only look at some variable in a function, or maybe even part of the variable in the function, and then still use it afterwards, I cannot do it if I pass it by value, because after I pass it by value, I cannot use it anymore. I passed the ownership to the function, and now it's not mine. I cannot use it. The second option was, so to solve it, we could use ref parameters, because if I pass the ref parameter, the ownership goes back to me after the function. But this doesn't give me the guarantee that the variable doesn't change. So a snapshot is somewhat in between, somewhere in between. If I want to use a variable, but guarantee that it doesn't change, so only a view of it, to get only a view of it, then I can use the snapshot. Snapshot is somewhat like a copy of the actual variable. It is passed, and the ownership of it is passed to the function, but I don't need the ownership of the snapshot. I only need the variable itself. And I can pass it to the function, get the guarantee that it doesn't change, and also use it later. So in this example, I have two snapshot parameters, the play with function. One is self, one is other. And as you can see again below, we can call skippy.playwith snapshot friend. So the add character is used to take a snapshot of a variable. So friend is the variable, add friend is the snapshot of the variable, and I pass it to the other parameter, which is actually of type snapshot of dog. And again, I don't need to write explicitly snapshot in the self parameter here. So I can just write skippy dot, although I need self is of type snapshot of dog and skippy is of type dog. Okay. Loops, I will not get into it. This is the syntax for loops in the language. We don't have yet for loops, which are long lasted. We will have sometime, hope that relatively soon. But you can do everything with this syntax. Yeah, I will just go on, and I will also not get into panics, but the idea is that if you want to exit the entry point, to exit your program with a failure from anywhere in your code, without anything to stop your more handling, then you can just panic with some data, and it exits the entry point with a failure. Named arguments. This is more another difference from Rust. So Rust doesn't have named arguments for functions. But if you consider, for example, this function foo, then in the first option without named arguments, you have add 3 true, false, true. This is very hard to understand. And with named arguments, it's much clearer. So, for example, you can know that the true here is for the parameter is high without going to the definition of the add function, which might be in a different file, for example. And we have a few forms of named parameters. The only restriction is that it needs to remain in the same order as the parameters in the definition of the function. But we can mix named parameters, for example, here the 3, and named parameters like here, which also have the basic form is parameter name colon value. Then we might have the same name for the value and the parameter name. And in this case, what we have is this shorthand, like in colon is new, which actually means is new colon is new. So in the cases, and there are many such cases, where you pass a variable name the same as the parameter name, you can just use this this shorthand. And it will also guarantee for you by the compiler that you didn't pass the wrong variable to the one variable to another parameter that you didn't mean. Okay. How much time do I have left?
I think you have at least a couple more minutes.
Okay, I will try to go over it quickly. This is, again, has a lot of details in it, but I just want you to see some of how it looks. So again, don't get afraid of the amount of code here. I don't want to get into everything, but the basic ideas are this is the way that we write contracts in Cairo for StarkNet. So actually, as I said, Cairo is a general purpose language, so you can write everything in it. And we also have in the compiler a dedicated plugin to write contracts. And this is the plugin acts on these attributes. If you can see, the hash character means an attribute, and the plugin sees these attributes and translates this code to something else. And it actually hides a lot of the complication from the developer. So this is the way that a developer writes a contract. So, for example, define a StarkNet interface, which has 2 functions. This means that the contract will have that will implement this interface will have 2 entry points, set and get balance. And as you can see below, we also actually implement the contract with the StarkNet contract attribute, and it has the storage. So these are the storage variables of the contract. So these are. I just hope that you know what storage variable means from other smart contract languages. If not, again, you can read about it. And then we have an implementation of this interface. And as you can see, this uses the Cairo language idioms. So we implement this, which is a trait, which is a StarkNet interface. And we have these implementations that actually also change the storage of the contract. And this API embed, ignore the V0 for now. This API embed means that these functions will go into the API of the contract. So other contracts will be able to call these functions when they call this contract. We also have events. So if I define events this way, again, it's not very important how, but the idea here is that it's very flexible. You can do whatever you want to define whatever events you want. And it's actually using enums and structs of Cairo. And then in the implementation of some functions, we can use self.emit and an instance of an event. And this will emit an event that will go into the operating system. Components. This is a new concept. We just released it last week, I think, or 2 weeks ago. The idea is that these are the building blocks for contracts. So if I want to have a component that can be used in multiple contracts or even by other components, I can write it myself, and then it can be embedded into, again, other contracts or other components that will be used by contracts. The idea is that components are not instances of something, are not startnet entities by their own, but they just define some maybe either interfaces or implementations for contracts to use. So once a contract takes this and that component, then it means that it exports some logic to the API, and it also can be used to implement basic things. So for example, if I have here an upgradable component, then it can be used by any contract to easily implement and upgrade functionality. So instead of writing the upgrade functionality again and again in every contract, I only need to do it once as a library, like any other library in any other function, language, sorry. And then I can use it in any contract that I want, which will give me the functionality of upgradability. This is the syntax for components. It's mostly similar to writing contracts, but it has some more ideas. Again, this is a little more complicated for explaining now, so I will keep it like this. But if you look for the recent posts in StartNet, then there are very good explanations of it because this is a new thing. This is the way to use a component. So in the contract, I want to use the upgradable component, for example. So I have this macro. This is a macro in Cairo, component exclamation mark, and I provide some parameters. So the path to the component, let's say it's defined here above counter contract. The name of the relative storage member, in this case, this upgradable, which is the storage of the component, and the name of the event that is relevant to the component. So as we can see later, we have this storage. This is a normal storage member. Then we have a sub-storage, which means I hold the storage that is defined by the upgradable component. So again, as I said, the fact that the component has storage doesn't mean that it's actually something, because it's only a library. And when I embed it into the contract, then I actually declare that I use the storage that the component defines. Same for event. I have one of the inner variants that is dedicated for the events of the component. It might not mean a lot to you, again, because this is a lot of information together, but again, the idea is that I can build things very modularly and very easily using these components. And then I only need to bring, so this is the syntax for impl alias. So it means that we bring this impl that is defined in the upgradable component into our context. And afterwards, we also apply the API embed on it, which again means that we embed the functionality that is in this implementation to the API. So if the component has an entry point, an external function, for example, upgrade, then now my contract will have the entry point upgrade without me doing anything. So I don't have anything saying I have a function name upgrade, but this brings me this function from the component. Okay. There is also a way to define dependencies between components. It's actually very easy. This is the example from before. I just added these two lines. So in the implementation, I just say that I also depend on an implementation to the other component, and then I can just use it. From my component, I go up to the contract. Because I'm a component, I'm not a real entity by myself. I need to be contained in some contract. So I know that if I'm contained in some contract, I can go up to this contract. And because I I wanted to have this dependency, I enforce this dependency, then any contract that has me has also the other component. So I can go up to the contract, then go down to the get the component, the other component, the ownable component in this case, and then use its functionality. So this is a way to depend on another component. And again, use the component. So this is a way to use components from components. Okay, there are some more things, internal functions, storage mapping in the storage, and ways to call other contracts. We'll not get into it. That's it, just a hint of what's coming up soon. Sorry, just hurry because I don't have a lot of time, or maybe even overtime. So we're in the process of developing strings or binaries. So you'll be able to use any string. For now, it's restricted. This is going to be soon, hopefully. We'll add for loops, as I said before. We'll add associated items in traits. If you know Rust, you might know what it means. Visibility, currently everything is public, but later we'll have pub to make things public. Iterators and more improvements to a lot of stuff. So stay tuned and follow what's going on. We advance in a nice pace, I think. Okay. Sorry about hurrying in the end. Now, if you have questions, or I don't know how many times I have for questions.
Yeah, we have time for 1 or 2 questions. Thank you, Yuval. So,
sure.
Do anyone want to ask any question? Or no, we have one.
Hey, so maybe I will start with the first one. Is like the Cairo or the assembly language the same like in Ethereum, that you pay for each instruction and for like all the storage that you use during like the code execution?
Yeah. So later, the proof, running the program and the proof will be longer if you have more instructions, and then you need to pay more. But it's a completely different scale than Ethereum, right? So any instruction here is equivalent to actually I don't want to say a number, but a very small portion of an instruction in Ethereum. So a few degrees less than what we have in Ethereum. So you have the concept of gas in Cairo as well, but it's a different gas, and you do need to look and to follow how much gas you use, but it's much. Each gas here is much less than each gas in Ethereum. And this is the whole idea of Starknet. So you do the same amount of stuff, but in much less gas.
Yes. So is it like easier to do an infinite loop and pay less, and then I don't remember, the verifier or the person doing the calculations will spend like more time on those? Or
yes,
is it like the gas or whatever like the currency is will drive to like zero faster than one would expect?
Yeah. So as you said, you provide an amount of gas that you're okay with paying. We can in the beginning you can estimate for a program how much gas it's gonna cost. It's not a guarantee because the state might change between the time that you estimated it and the time that you run it. But after you estimate it, you can, I don't know, multiply it by 2 or whatever you want, or just put a very high number, and then it runs. If it finishes without draining the gas and it succeeds, then great, you will have the proof that it ran and the state changes from one state to the other. And if it failed from another reason, or from the fact that the gas is over, that you are out of gas, then we'll prove that we actually ran it, and will not we, the prover. The prover will run it and charge the fee. So if you want to do it, you can, but you're just gonna pay not an infinite fee, the maximum fee that you're specifying.
Yeah, sure. And the other question is, because like Cairo is a high-level language, and because you pay with gas for like the operations and so on, so does like the Cairo itself does any optimizations that would reduce some calculations? Like for example, you've declared a variable, so you pay something for it, but then you don't use it. Like, does the Cairo deletes like this code in the low-level assembly language, or just it stays there and it's like the responsibility of like the person, you know, writing the code to know that?
Yeah, so this is a great question. So we do a lot of optimizations. Of course, there's always room for more optimizations, and as we are developing Cairo, we're adding more and more optimizations for stuff. Eventually, because we always create safe CASM, again, an assembly that is always can also be proven. Inherently, like any other high-level language that is translated or compiled to low-level language, may be less efficient than the lower-level language. So you are able to take the assembly and change it, or write the assembly yourselves. But in the case of StarkNet, you are able to only provide safe. The contracts are provided in Sierra. So the Sierra means that the compilation goes to a safe CASM. So you need to either write in Sierra, or maybe in the future you will be able to somehow do it with CASM, but you'll have to somehow show that this is safe. So this is going to be much harder, but it is theoretically possible. But yes, we do a lot of optimizations, and even after the cost that it does cost to compile from a higher level language to a lower level language, it turns out it's much more cheap in scales rather than Ethereum. Did it answer the question?
Yeah, sure. That's it. Thank you.
Thank you.
All right, I don't think we have time for more questions, unfortunately. Thank you, Yuval, for your presentation. And now Michał from L2Bit will introduce us to challenges in Ethereum smart contract research. So off to you.
Thank you. Bye.
Już? Oh, okay. So, yeah, challenges in Ethereum smart contract research and how to overcome them. Cool title. It was written by ChatGPT. Yeah, but so my name is Michael. I work in L2Bit, and for the last half a year, I was working on our tooling system. So we do a lot of research on different contracts, and yeah, we want to make sure that the information that we post on our website are as accurate as possible. So yeah, we do a lot of Ethereum smart contract research. So what's the problem? So in my opinion, the biggest problem with researching systems on blockchain in general is marketing overload. So blockchain is a big industry, and you can make a lot of money quite quickly. So there's a lot of people who want to make money quite quickly. And everyone wants to be the first, everyone wants to be the best, and so on. And the solution to that is to trust the code, not the claims. And that's what we do at L2Bit. And so basically, we make sure we go straight into the smart contract code, and we verify with what's available on blockchain. And yeah, so you can see here that Chroma is not stage 2 rollup, for example. So how do we do that? And first thing first, Etherscan. How many of you have heard about Etherscan? That's a substantial amount of people. That's fortunate. So yeah, Etherscan is the first point where we start smart contracts research. And yeah, let's actually go to the tab here I have open. Is it better? Maybe. Okay, so here I have an example of a very simple smart contract that probably all of you know. It's a wrapped Ether. It's a ERC20 token, and if you go to the website, to Etherscan website, to the address of the token, or even the token tracker here, you can go here to the contract tab and see this code. Okay, amazing. So, for example, here we can see that there is some name, wrapped Ether, some symbol, the deposit function, for example. Okay, so we can see it's payable, all that good stuff, right? We can read the code, which is actually quite cool. We can also read the contract, which is basically calling the contract, and which, I mean, Etherscan under the hood calls this contract on the blockchain and gives us the response from RPC. So, for example, here we can see that name is wrapped Ether, total supply is this big number, decimals, and so on and so forth. And this is fine, right? The code here is quite readable, and but there are bigger constructs than this one. This one is, I don't know, it's basically 80 lines of code. But let's see maybe another one. Oh, not like this. I wanted to go here. Okay, so let's see. Uniswap v2 factory contract. So if we want to go here and actually read this contract, this is quite challenging. There is some interfaces in the beginning. This window is actually small. There is no syntax highlighting. So the next step after, so with, for example, bigger smart contracts than wrapped Ether, we use dev.code. How many of you have heard about dev.code? Nobody, really? Okay, that's interesting. So I was expecting a different answer, actually. So dev.code, it's this is a product from one of our co-founders who don't work for us anymore. But you can actually do it. You can access it really easily. You just go to the address bar and change the .io to .dev.net. And what it does, it actually opens a VS Code instance in your browser where you can browse the code of the smart contract much more easily, right? So here you can see that, I mean, it's first of all way more familiar. That's how I write and read code every day. And the syntax highlighting is way better. And it can actually support multiple contracts, but we'll go to that in a second. So that was our first example of the dev.code, and I highly recommend that, especially that you can just create a browser bookmark here, which is basically a really simple JavaScript that changes the location href with some regex, and you can go to dev.code from any website. From any Etherscan contract address, and yeah, this is quite cool. Highly recommend. So, but there is a problem with upgradable contracts. So, upgradable contracts. Who here heard about upgradable contracts? Okay, that's quite a lot. So. There are problems with them, and I will just show you how. And again, not like this. How a website, an Etherscan website of an upgradable contract looks like on Arbitrum. So first of all, when I go to this is an Arbitrum token, okay? So this is the Arbitrum token implementation on Ethereum. And here, when I look at the contract name, is transparent upgradable proxy. And I want to see where is the ERC20 implementation, right? Because it should be ERC20, but it's really hard to find it here. And the thing is that this contract is not really an ERC20 contract. It's storing this logic in the implementation. So here is a simple diagram of how probably the most popular ERC 1967, EIP 1967 proxy looks like. So basically, you have this contract that's deployed on Ethereum, and it uses some other contract. It uses the logic from other contract using the delegate call. And the delegate call is an opcode that allows this implementation contract to actually run with the storage of the proxy contract. So whenever the deployers, the owners of the Arbitrum contract would like to change the implementation, they can do that. I'm not gonna go to the security assumptions of this solution, because that's completely another topic, but it exists and people use it extensively. So it's worth knowing what's happening there. So going back to this page that shows us the code, you remember I showed you with wrapped ether that we can read contract. And here, if I go to the read contract page, it doesn't work because the proxy contract doesn't actually include any logic that's available for us. It's only available for the admin of the proxy. So here we have another tab, which is read as a proxy, okay? And we can actually see here that total supply is this big number, symbol is ARP. Yes, but the important distinction here is what we can see on the address of the implementation. So this is the actual contract that stores the logic of Arbitrum token. And if we open it in new tab and go here and read the contract here, and we go to total supply, it's 0, okay? Because as shown on this diagram, this implementation contract, it's not using its own storage. It's using the storage of the proxy contract. And Etherscan is asking the storage of this contract, which obviously is 0, which is a little bit misleading. This is actually really cool from Etherscan that you can do that, because it abstracts from you this proxy pattern, and you can actually read the important params on the contract page. So this is about the 1967 proxy. But there is also the diamond. How many of you have heard about the diamond proxy? Okay, so this is actually not that hard. It's a little bit more complicated, but basically the idea with the diamond proxy is that you have the proxy contract, which is called the diamond here. And it, in its storage, stores a mapping of function signatures to facets. Facets are basically implementations, but there can be more than one implementation, and the amount of facets can be increased basically anytime. So what's happening here? If a user calls a transaction on a function with signature 0x456, this diamond contract will look into its storage and will find in which implementation or in which facet this function signature logic exists. Okay, So, for example, for here for the signature 0x456, we can see that the facet is 0xabc. So it will call this exact facet to actually use the logic in this facet. Any questions about that? Yeah, you can just.
Yeah, I will just ask. It's like each function, like the facet, separate contract. So a contract works just has like single interface. It's a function, and you have to deploy all of them to. Use
No, normally not. Normally there is multiple functions for each facet. And here, but here I just showed 3 functions because I was too lazy to draw all of them. But yeah, basically it allows you to modularize your smart contract system. So for example, and you can actually divide what logic should be in which contract, right? So there is, for example, contracts that are responsible for messaging, or contract that's responsible for state validation, or anything you want, right? So, but because and also one other thing that's important to know about Diamond Proxy is that it allows there is a hard cap of how big the smart contract can be on Ethereum, and if you are storing multiple facets, then you can basically go up to infinity, right? Because you only store the mappings on your contract.
And maybe other question, where does the name Diamond comes from?
So the idea here is that you can have multiple proxies that are using the same implementations, and this actually starts to happen. For example, with OP Stack, it's not yet developed, but for example, OP Stack is a stack that is the optimism stack. That's okay. Maybe I'm going to the tangent, but basically, I think it's coming from the shape of how you can draw the diagram here, but honestly, I'm not sure. So I will not make it up, but that's a good question. So yeah, so that's kind of how Diamond works. But what I want to remember from you is that the Diamond does not store any business logic. The Diamond, so the proxy contract, stores only the mapping for the functions. So all the business logic, all the logic that we are as users are interested in, are in the facets. So yeah, let's see how Diamond contract looks at, how does it look on Etherscan, right? So yeah, here we can see that there is some code, and it's in fact Diamond Proxy. And we can even read the contract. Okay, there's actually not available ABI, but we can read as a proxy. And there is only 4 functions here. Yeah, some get name. I'm not sure what's that. So, but what's happening here is it's only finding one implementation of this contract, but long story short, it's not. There's multiple facets, or it's calling it here implementation, but probably something in Etherscan's way of showing us the implementations here is wrong. They are definitely using some heuristics to make sure that there is something. So I don't know how they are finding the implementations, but I can show you something cool. So yeah, unfortunately, Etherscan with our Diamond Proxy is not really that effective. But mind you, we are from L2Bit, and we are supposed to find and read their smart contract code. So at one point, our lead researcher was like, "Okay, come on, guys, we need something better." So then in the darkness of our basements, there was created one tool to rule them all, and it's L2Bit Discovery. And I will just show you a simple. Is it visible? Yeah, I think it's visible. So we created this tool. It's called Discovery. It's available on NPM. So it will make our smart contract research easier. So And I will quickly show you how powerful it is on example of the zk-sync contract of the Diamond proxy. So here is a simple config where basically the only important part is that I will actually comment it out, is that this I just create initial addresses map array, which tells this system where it should start. And when I run it, I will explain it to you quickly how it works. So you can see here it was analyzing this address for a second, right? So what it did is it first called Etherscan to find the ABI of the contract. Then it used some a set of our heuristics to make sure that this is in fact the Diamond proxy. And then, because this is standardized, we were able to get all the facets addresses, and actually find all of the available functions on those facets, and actually get their get the results of the calls of those functions. And you can see it here. This is definitely harder to look at than Etherscan, but this is very powerful. So you can see here that the address is the same, is zk-sync, but here we can see that there is not one facet here, 6AA, right? But there is actually 5 that are actually used by the zk-sync smart contract. And here there are the addresses again. And here this is the mapping that I told you about. So you can see that this contract stores the logic for those particular function signatures, and so on and so on. There is and this actually tells the proxy contract where it should ask for the implementation of the logic. And here we can see all of the values that were called that we called for. So we called for all the get allow lists. So this is another contract, and like this we are sure what is the state of the state of the smart contract. It's not all of the storage, because it's we weren't able yet to plug something like like if.storage, but this is something that we can work with. And also a magic folder appeared here, which stores all of the contract code from Etherscan. So this is very powerful, and it actually allows us to read the smart contract code locally, so we don't have to use dev code anymore. And that's how our discovery makes our life easier. What's additional is that for each Ethereum address that's discovered during this process, we basically run it again on this particular address. So, for example, for the allow list, it was also discovered. So here we can find that the allow list contract is immutable. It was deployed on this timestamp, and that those are the values that are stored on the allow list. And yeah, that's basically it. Now it's time for questions. Any questions? Come on.
Are there any important patterns besides like the diamond pattern and the previous one was just
There's many. There's
and do you have tools for like each of them, or like just does the discovery works just for the? I believe it's not just for the diamond proxy, but
no.
It's probably for like.
It's basically for anything. I mean, it should be so. Anything that we are discovering, and this is the list of all of the projects that we are discovering, they often have different. So, for example, it can detect EIP 1967 proxy. It can detect some. There is some weird Arbitrum proxies that it also is able to detect. I don't know if I can show it to you here, but basically there is a really long list of the heuristics basically that we implemented to make sure that we can discover. We can also discover the Starkware diamond. We can because this diamond is even better in terms of working with. So basically, we are improving the system as we go on, and there is a lot of different patterns.
Like just off the top of your head, how many, if you were like to guess?
I would say it's so. Right now we are supporting, let's say, for the proxy pattern around 20. But for example, we are also able to detect gnosis safe. I mean, this is not too hard, but yeah, I would say that there is around 20 of the patterns that are discovered automatically, and but also we have custom handlers. So for example, if some variable is immutable, or maybe it's immutable and it's set in the or it's set in the constructor code or in the constructor call, or it's private but there is an event. We have handlers for all of them. They require configuring in the config.json, but it's definitely. I mean, this is the best tool I have worked with. I haven't found anything better. If you have something better, please tell me, because I'm doing it almost daily, and it definitely have some drawbacks. But yeah, but.
Yeah, that's. Thank you.
So actually, there is one bonus thing. What the hell happened here? So wait, where is that? It's here. So, and this is more like a quiz. So I really hope that somebody will find it. So we have this smart contract, and I stumbled upon it I think 2 weeks ago. It's used by Optics Bridge as upgrade beacon, and the weird part here is that Etherscan thinks is some kind of token with this weird name. Yeah, and actually our discovery also broke on that, so we had to fix it. But I have a quest for you to tell me why it happened. And a small hint, the answer is on the screen right now. Anyone has an idea? Okay, so what does the fallback function do? And also, this fallback function is the only function that's available in this smart contract. Do you know what fallback function is? Yeah?
I have an idea.
Yeah?
Because they neutralize token name.
Yeah, again, I didn't...
They neutralize token name, and they got that fallback.
Yes, yes. But what does this fallback return? Okay, so maybe I will walk through it quite quickly, and it's really weird. I have never seen this pattern before. So fallback function it's a special keyword in Solidity that's executed anytime somebody calls a contract with a function name, with a signature, with a function signature that doesn't exist on this contract, okay? So basically, if you call this contract with any signature, you will go to the fallback function, okay? And then, if the message sender is at the controller, which probably we are not, because that's just one smart contract and not us, and we are not even signing this message because we are just doing a simple call. If the message sender is the controller, is not the controller, go to assembly, load the first variable, and return it. And actually what happens here is that if it says here actually on the screen, if not called by the controller, load the implementation address from the storage slot 0 and return it. So this name is actually just the implementation address that's returned by this beacon, but Etherscan tried to decode it in UTF-8, so that's why it's so weird. And when reading smart contracts, and people have different really weird ideas, and you have to be prepared for something like that. And I just wanted to include it because I thought this is really funny. Okay, and yeah, that's all from me. Thank you, everyone. My name is Michał Sobieraj-Jakubiec. You can add me on Strava so we can race a little bit, or write me an email or something.
So I don't know. Do we have any questions or? Yeah. Okay.
Just came up with this question later on.
No worries.
Have you thought about publishing Discover as a website, like Etherscan, or like integrating it into Etherscan even?
Yes, we have thought about it, but honestly, maybe in the future. Right now, it is available as an npm package, but making sure it's actually usable for users, and it's really simple. It requires a lot of effort, and we have a lot of things to do right now. But maybe in the future, definitely. We are actually using it multiple projects, and yeah, we are basically improving it as much as we can because that's thing that we use daily.
Yeah, gotcha. Because it looks very cool, and I believe it would be very nice for other people in that form.
I'm glad you like it.
Do we have any other questions? We have time for one, I think, maybe. All right. Okay.
Where we use the discovery? I know about your project L2Bit from previous conference, and maybe any other cases.
So I mean, right now it's our internal tool. So we use it mostly for research, but we also and it was built for research. It's a very unoptimized JavaScript script that's just running and then trying to get all the information that it can. But actually right now we use it in a cron job on our backend, and it notifies us any time that something changes. So actually you can go to our public Discord, and there we have update notifier tab, and it notifies us anytime some important value of the contract changes, so we know that we have to update our website.
Yeah, I see. Thank you. And as idea, you can share, you can provide it for some other projects too, like Etherscan, to help them be better.
That's possible. As I said, maybe in the future. Right now, it's it works. It's powerful, but it's very slow. So maybe it's not on the. It's not possible for Etherscan to use it. But maybe in the future we are actively improving it.
Yeah, I see. Thank you.
Thank you.
All right, I don't think we have time for more. So thank you, Michał. And
Thank you.
now Marcin from Software Mansion will join us for the talk about everything forking.
Okay, hi everyone. I'm Marcin from Software Mansion, and I'm working at Starknet Foundry team. And recently I've developed a solution about forking in the tests, and I wanted to share my knowledge with you. But firstly, we have to explore some details about what the forking even is. And what is the fork? The forking in the blockchain context is hard to define because there are different types of it. And but if someone usually talks about forking in the blockchain context, he means that there was a split in blockchain underlying protocol. But it's only the one type, so let's find out what other types are. So the fork splits into code-based fork, live blockchain fork, and test-level forking. We will talk about test-level forking at the end. And live blockchain fork splits into some other kinds we will talk about later. So let's jump to code-based fork. Code-based fork is basically copy-pasting the code of some cryptocurrency, some blockchain, and running it on our site. And as you can see at the slide, there was a Litecoin, and then was a Lucky Coin, which was the fork of the Litecoin, and there is Dogecoin, which is a fork of Lucky Coin, and it shows how code-based forks really works. They took the code of some cryptocurrency, apply some changes to optimize it, maybe to become faster, and just run. Dogecoin was a little bit different because it was a joke at the beginning, but it's very popular now, and it still works. So the other kind the other group is live blockchain forks, and live blockchain forks happens when there is some blockchain, like let's say Ethereum, and developers or community decide that they want to apply some changes, and the blockchain splits into two ways, and let's see what are the ways. First type of it is accidental fork. It happens when it happens often, and it is when two miners mine the block at the same time, and the chain, which was one at the beginning, splits two different or maybe more parts. But after some time, when nodes decide which chain they want to use, the shorter one will disappear, and the other nodes will jump into the longer one. And the other type of fork is intentional fork. And this happens when the community or developers want to add some new features, fix the bugs or revert unwanted transaction, which is tricky because in the blockchain we can't do it almost every time, but yes, almost all time. But it happened in the big cryptocurrency. And intentional fork splits into two types of forks. Soft fork, which is minor software update. It's backward compatible, so it means that the old blocks can, the old nodes, nodes with old software can still verify new blocks and verify them as correct. And it also can add some changes to the protocol, but will rather narrow them, not enlarge. And the other type, most important, I think, is a hard fork. It happens when when the changes are big and it's not backward compatible. Old nodes can't verify new ones, and they have to update their software. And it usually, new cryptocurrency is created, and full nodes have to decide if they want to update their software and go the new path, or live with the old one, and that's why the blockchain splits, because some nodes don't want to split, don't want to update, and it's usually connected with community split, because first, I think most famous one is Ethereum Classic. It happened when the DAO organization contract was hacked on the Ethereum, and community had to decide if they want to revert that transaction and make a hard fork and go this path, or live with old rules and don't revert it. And someone really didn't want to revert it, so Ethereum Classic happened, and it is the old version of Ethereum, and the chain which we know as Ethereum now is the new version on which hack is reverted. I don't know if it's correct, it's maybe a philosophical question, but they did it. And the second example is Bitcoin Cash, and here the community and developers couldn't agree on the issue with slow and expensive transactions. They created another blockchain, Bitcoin Cash, which is a hard fork of Bitcoin, and on which blocks are bigger, so transactions are faster and fees are lower. And it's doing quite well. So it was, let's say, a good hard fork. Ethereum Classic wasn't. And let's jump to, I think, most interesting part, especially for me, because I'm working on it. The test level forking is connected with writing test. And sometimes we have a test code, and we want to run it on the real state of real chain. So we have live blockchain and test code. We merge it, so run the test code on the live blockchain, or the fork of this blockchain, and we have fork testing. And how is it achieved on Ethereum? There are three biggest tools to test smart contracts on Ethereum. It's Truffle and Hardhat. in which you can fork a real network and run it on your machine, and then run your tests on this forked state, but you can't really configure it. You can only type truffle test on the local network. So it's not really flexible, but in Foundry, every test can have a different network which is forking, and you can configure it inside the test. And it's something called multi-forking, but I will talk about it later. And in Truffle, you have to use something called Ganachi. It's a local node, and you can fork a real network with it, and then configure it in the Truffle config.js, as far as I remember correctly, and run those tests on the state. However, in Foundry, you can configure it inside the test, so and even change forks inside this one test. It's helpful in developing some bridges between networks, between blockchains. So you have mainnet fork and optimism fork, let's say. You can set up it with create fork function with some URL, and then select it inside the test, and then select another fork and play with the state between those two forks and interact between them. And you can also choose the block number. In Foundry, it's called roll fork. And we have Starknet Foundry, which I'm developing now. And we have some syntactic sugar for the forks. You can use the fork attribute and configure with URL and block ID, and then simply use the state inside your test without any creating forks or selecting it. As you can see, we take some address from the real network and call getBalance function on it and get some value which we didn't set previously. And we can play on top of it and locally change the state of this network. And what does forking do under the hood? And there are RPC requests to full nodes and local and remote state. So let's go through the diagram. Firstly, we have to check if we cached those calls, because if we cached it, it will be much faster, because calls to RPC nodes are slow. If yes, we can just return the data, but if not, we request the data with block number and URL, set up some worker if it doesn't exist, and create a request, and wait for it. Store the result in the cache. It's really important because we don't want to make more requests with the same data. And yes, that's it. That's pretty simple. But we do not fork the entire blockchain. We only take some parts of it which we want in the tests. And we share this data between different tests. So it will be slow at the first time, but after in the second run, it will be fast because we will only read our local state. And there are some multi-forking ideas which I have. And if you know anything about multi-forking, head to me because we can talk about it, because only in the design area. But the idea I have is that there are some states for different networks, like mainnet state, testnet state, and another testnet state, and even more. And there is shared state in which we will keep data we want to share between different networks, between, let's say, mainnet state and testnet state. Before the call, each call, we will merge the testnet state and shared state and run the call on top of it, and then split those states and separate them completely. Okay, any questions? Yes?
I have a question about code level forking. Just by example, like if I understood correctly, if I take the Bitcoin repository, clone it, and compile, I assume I won't receive the another cryptocurrency. I will just compile the full Bitcoin node, and it will be connected to another Bitcoin nodes. If my assumption is correct, then what is the minimal changes should be done in existing code in order to create new cryptocurrency?
I think it's only the name. So if you change the name, you have another cryptocurrency and you are owner of it.
But what if nodes will be connected one to each other, or they won't be connected because name mismatch? It is just some kind of check on code level, or how it works?
They won't be connected because it will be another blockchain. It won't have any history. Your node don't fetch the data from the Bitcoin. It will start from the beginning.
So name is kind of unique identifier of cryptocurrency, and like this is enough. Okay.
I think so, but I'm not the expert on this kind.
Thank you.
Sorry, do you know any good fork, so-called? Because we have, like, for example, a Bitcoin Cash or Ethereum Classic, which is, in my opinion, is not so good and not provide any new ability for users.
Okay, I agree that Ethereum Classic is not a good fork, but Bitcoin Cash provides something new. I don't know really much about it, but it's faster and cheaper. But I only know that they increased the block size, which can affect decentralization. So it won't be so secure, I think.
But do you know any so-called good forks?
No, not really.
Okay.
I mean, I may be taking stupid things, but aren't Ethereum upgrades like good forks, essentially?
Yeah, but they are still the same chains, but yeah.
Implementation-wise,
yeah,
it's basically a fork. So that's a good fork or not fork.
For example, a segment for Bitcoin. I think that an example of good fork is a soft fork of Bitcoin in 2017, as I remember. It was a hard fork for Bitcoin Cash, as I remember, because main network of Bitcoin was changed to SegWit, to segregated witness validation process, and as you mentioned, some developers not wanted to take part in that, and they continued in Bitcoin Cash, as I remember, and I think it was a very good upgrade, and it was a hard fork and soft fork in main history of Bitcoin.
Right. So probably there are some good forks. Do we have any other questions?
I've got a question about hard fork attack. Is it possible somehow to attack the network if you, for example, got enough miners that who will support your network? So in the end, you can be an owner of a main network, as far as I understand.
You talk about the situation when you have some group of people which want to fork their
Ethereum, for example,
yeah.
and they got more miners than 51%.
Okay, it's probably possible, but Ethereum is huge, so
Yeah,
in
yeah,
real
okay.
world,
I mean,
it
is
won't
it possible?
work.
Is it any, I don't know, as far as I know, in Ethereum 2.0, they trying to defend themselves when you supporting another forks, you lose your stake somehow. Do you know some details about that?
Oh, maybe, but I don't know really much about the staking.
So this is actually a quite hard question, and it touches more, in my opinion, on like, so why does Ethereum even have value? Like, I mean, the idea here is that you as a node operator, you are basically choosing which fork you are following. And the moment that the network is attacked, and let's say that people know about it, it kind of loses value. So probably the network that will keep having value would be the one that's not attacked. So it's definitely possible. You can run your own node and say in your node that you own 1,000 Ether right now. You can do that, but none of the validators will actually accept the state from your block, and so it will diverge, right? And so it would be this kind of attack. And I mean, obviously, if you had over 51%, that's just 51% attack. You don't have to fork. But I think what you mentioned about Ethereum 2.0, Ethereum with proof of stake, the idea is that if somebody gathered enough staked Ether to actually attack the network, the network, so social consensus of people who run nodes could say that, okay, this guy is actively attacking the network, we'll just delete the amount of money that he has on his account, and we'll just follow without him. Sorry?
Who decided?
That's social consensus. So basically people on forums, on Twitter, like you have to, as people who run nodes, so like the idea is that everyone who is the user of Ethereum should be able to run a node. That's obviously not the case, but basically the validators, people who run nodes, who store the Ethereum state, they are kind of deciding what's the state, right? They can follow what says in the code, but they can also follow something else. They can upgrade their code, and you know, it's a very hard philosophical question, and not that technical, in my opinion.
When you mentioned about the hard fork, there was a point when a fork happens due to community split.
Yeah.
And what happens with the transactions written in a history? With this fork, does a new fork goes from scratch, or does it have the full history of another one, or something else? Can you explain, please?
It can have a full history, or they can reverse some transactions, like in the Ethereum. So it's up to the nodes, really.
And what about, I don't know, the value of the coins in such case? If people start, I don't know, if I see it correctly, owning coins in both forks. So what happens?
It will probably decrease. that's it.
So maybe I have a question about like the hard fork. So when you do the hard fork, some like amount of nodes have to agree, for example, to support certain like, I don't know, newer version of transaction, whatever. But isn't like the case where the blockchain is not that secure? Because the main like power of a blockchain is that you have a lot of nodes, so you have to have a lot of processing power to modify blocks and so on. But when the hard fork happens, for example, somebody may want to spawn tons of nodes that will modify the transactions on their account. So like it's better for them because they have like the 51% of the power. They can do all the stuff. Isn't like the least like secure part of the process. So when a hard fork happens, a lot of stuff can go wrong basically because somebody spawned so many nodes that the network grew so big, but on their advantage, basically.
Yes, it can happen, but the fork can be abandoned and they will stick to the old one, and they can prepare for such an action in some way. I don't know, maybe have a period of time when the nodes can update, and then hard fork the blockchain again, and if it won't work, they can do it one more time and one more time. So
basically, if like nobody notices, it can stay like that. So somebody manipulated it, transferred some funds with like some malicious transactions, and it keeps that way until somebody notices. They do the hard fork, leave that fork, and it's like doing.
That's a good question. I don't know such a situation, but maybe it can happen. But I think Ethereum Foundation and community somehow prepares for such a situation, but I don't know the details.
Yeah, thank you.
I guess we have time for maybe one more question, if somebody wants to ask it. Okay.
Okay, so let's go to the last slide. If anyone wants to have a talk, please scan the code, and there's a form. You can fill it, and let's meet in the next meetup. That's all for me. Thanks.
All right. All right, so that was all for the talks for today. We'll have pizza in a minute, or I think it's already there. So feel free to stay with us for pizza and beer and just networking. Thanks for attending the second meetup we hosted here. There will definitely be more. I think if you're here, you're already following us on Twitter, Instagram, or whatever. So just continue following us, and we'll be posting more info about upcoming meetups. And thank you for attending.
Yeah, and pizza is here.